In ancient Greece, mathematicians proposed three famous problems of geometric construction that were considered the most challenging topics in geometry at the time. These problems required constructions using only an unmarked ruler and a compass. The problem of doubling the cube asked for the construction of a cube with a volume double that of a given cube. The problem of trisecting any angle required dividing any given angle into three equal parts using a ruler and compass. The problem of squaring the circle asked for the construction of a square with an area equal to that of a given circle. For thousands of years, geometers tried but could not find solutions to these three problems. It wasn't until the rise of algebra that people discovered that these problems are, in fact, impossible to solve using compass and straightedge. To illustrate the impossibility of these problems, this video will guide you through an in-depth understanding of the essence of ruler and compass constructions and introduce relevant algebraic concepts, explaining how algebra proves the unsolvability of these problems. On a number line defined by a 0 point and a unit length, if a number's position on the number line can be accurately marked using ruler and compass constructions, it is called a constructible number. For example, we can use a compass with a unit length radius to accurately mark the positions of all natural numbers on the number line. Thus, all natural numbers are constructible numbers. We can also replicate the unit length to the left to accurately mark the positions of all negative integers on the number line. The set of natural numbers combined with negative integers forms the set of all integers. Therefore, all integers are constructible numbers. Consider all integers as a set. All numbers on the number line form another set, the set of real numbers, of which integers are a subset. Since all integers are constructible, the set of constructible numbers lies between the set of integers and the set of real numbers. If we can accurately define the set of all constructible numbers, we can determine whether a construction problem can be completed using only ruler and compass by checking whether the desired measurements fall outside the set of constructible numbers. For instance, in the problem of squaring the circle, assume the circle's radius is of unit length. Since the requirement is that the area of the square equals that of the circle, the side length of the square constructed with ruler and compass would need to be the square root of pi. If the square root of pi is a constructible number, we could mark this length on the number line using a ruler and compass, thereby drawing the square. If the square root of pi is not a constructible number, it means this problem cannot be solved using ruler and compass constructions. Now, the key question becomes how to accurately define the range of constructible numbers in order to assess whether certain lengths, such as the square root of pi appearing in the problem of squaring the circle, are constructible. Numbers that can be accurately marked on the number line using ruler and compass constructions are defined as constructible numbers in a geometric sense. However, this definition does not provide us with an effective way to determine whether a given number is constructible. We need to refine the definition of constructible numbers from an algebraic perspective. Humankind's understanding of numbers began with integers and expanded from integers to define the entire set of real numbers. We will follow this progression and highlight the algebraic definition of constructible numbers. After integers, the first numbers recognized were rational numbers, which are an extension of integers. Numbers that can be obtained from integers through a finite sequence of additions, subtractions, multiplications, and divisions are called rational numbers. -4 is a rational number, 1/3 is a rational number, 1.8 is a rational number, and 36 divided by 7 is a rational number. These numbers, represented as integers, fractions, and decimals, are all rational numbers. Rational numbers have a notable property called density. Between any two rational numbers on the number line, no matter how small the interval, there is always another rational number. Due to the density of rational numbers, it might intuitively seem that all numbers on the number line are rational. However, this is not the case. The length of the diagonal of a square with side length 1 is the square root of 2, which cannot be expressed as the ratio of two integers. Therefore, it is not a rational number. The circumference of a circle with a diameter of 1 is pi, which is also not a rational number. These numbers are called irrational numbers. In the set of real numbers, numbers that are not rational are called irrational numbers. It is said that the ancient Greek Pythagorean school first recognized the existence of irrational numbers. However, for thousands of years afterward, understanding of irrational numbers remained limited. It was not until the advent of modern algebra that irrational numbers were further classified, enabling the accurate description of constructible numbers. Constructible numbers include some irrational numbers, but do not encompass all real numbers. The algebraic definition of constructible numbers is similar to that of rational numbers. Numbers that can be obtained from integers through a finite sequence of additions, subtractions, multiplications, divisions, and square root operations are called constructible numbers. Compared to the definition of rational numbers, this one adds the operation of taking square roots. You might wonder why this definition describes all the numbers that can be constructed with a ruler and compass. We will save the explanation of this question for the end of the video. Constructible numbers form a larger set than rational numbers. The irrational number square root 2 is a constructible number, and the golden ratio, 1 plus square root 5 divided by 2, is also a constructible number. It is important to note that these operations can be nested. For example, square root 17 is a constructible number, and square root 34 plus 2 times square root 17 is also a constructible number. The number under the square root does not have to be an integer and can even be an irrational number. Gauss proved that the cosine of 1/17 of a full circle can be calculated using integer additions, subtractions, multiplications, divisions, and square roots. Thus, the cosine of 1/17 of a circle is a constructible number. This means that it is possible to construct 1/17 of a circle using only a ruler and compass, which further implies that a regular 17-sided polygon can be constructed using only a ruler and compass. In addition to constructible numbers, algebraists have defined another set of numbers called algebraic numbers. Algebraic numbers include all constructible numbers, but some algebraic numbers are not constructible, such as the cube root of 2. Algebraic numbers are defined as numbers that are roots of polynomial equations with integer coefficients. Algebraic numbers do not cover all real numbers. There is a part of the real number set known as transcendental numbers. The number pi and Euler's number e are both transcendental numbers, meaning they are not roots of any polynomial equations with integer coefficients. With this algebraic knowledge, revisiting the problems of doubling the cube, angle trisection, and squaring the circle becomes much clearer. In the problem of doubling the cube, we seek to construct a cube whose volume is double that of a given cube. Assume the given cube has a side length of 1, making its volume 1. The volume of the target cube is 2, so its side length is the cube root of 2. As mentioned earlier, the cube root of 2 is an algebraic number, but it is not a constructible number. Therefore, we cannot construct a cube with a volume of 2 using ruler and compass constructions. In the problem of squaring the circle, we aim to construct a square with the same area as a given circle. Assume the radius of the circle is 1, making its area pi. To construct a square with an area of pi, its side length must be square root pi. Both pi and square root pi are transcendental numbers, not constructible numbers. Therefore, we cannot construct a square with an area of pi using ruler and compass constructions. In the problem of angle trisection, we need to precisely divide any given angle into 3 equal parts. Assume the vertex of the angle is at the origin. Using the unit circle, if we know the cosine value of the target angle, we can construct the angle. Thus, the ability to construct a given angle is equivalent to whether its cosine value is a constructible number. The cosine values vary for different angles, and as the angle changes continuously, the cosine value also changes continuously between -1 and 1. When the cosine value of the target angle is a constructible number, the angle can be precisely constructed using ruler and compass methods. When the cosine value is not a constructible number, the angle cannot be constructed precisely using these methods. Therefore, for any given angle, some can be trisected while others cannot. The problem's requirement to trisect any angle is impossible. Defining constructible numbers algebraically, and using this definition to determine whether the geometric quantities in the target figure are constructible, is the key to deciding whether a ruler and compass construction problem is solvable. However, in the previous video, we overlooked one important question. Why can, and only can, ruler and compass constructions produce constructible numbers? To rigorously answer this question, we need to prove two things. First, ruler and compass constructions can perform addition, subtraction, multiplication, division, and square root extraction. Second, ruler and compass constructions cannot perform operations beyond these. Next, I will demonstrate how ruler and compass constructions can perform addition, subtraction, multiplication, division, and square root extraction to prove the first point. As for the second point, I will leave it for you to think about, and your thoughts in the comments section for discussion are welcomed. Before performing algebraic operations with ruler and compass constructions, let's first look at two basic construction problems: perpendicular line and parallel line. Given a line L and a point O, how can we draw the perpendicular line to L through point O? Draw a circle centered at O with a sufficiently large radius, such that it intersects the line at 2 points, A and B. Next, draw two circles with centers at A and B, both with the same radius. Connecting one of the intersection points with point O gives the perpendicular line to L. The corresponding proof is not complicated. Since the three sides of triangles OAC and OBC are equal, these two triangles are congruent. Therefore, the line OC is the angle bisector of angle C. Because triangle ABC is an isosceles triangle, the bisector of the apex angle is perpendicular to the base. If point O lies on the line, this method still works the same. Once we can construct a perpendicular line, constructing a parallel line is not difficult. Draw the perpendicular line to L through point O. Then, draw the perpendicular line to L through any point A on L. Using a compass, copy the length of BO to this perpendicular line, obtaining point C. Now, connect C and O. Since the quadrilateral shown in the figure is a standard rectangle, the line OC is parallel to L. After mastering the construction of perpendicular and parallel lines, we can proceed to perform algebraic operations like addition, subtraction, multiplication, division, and square root extractions with ruler and compass constructions. The positions of points O and I, representing 0 and 1 on the number line, have already been marked. A and B are two known numbers on the number line. We will first perform addition and subtraction with them. With A as the center, draw a circle with a radius equal to the distance from 0 to B. This circle intersects the number line at 2 points, A plus B and a minus B. Therefore, we can use ruler and compass construction to create the points for A plus B and a minus B. Can we construct a multiplied by B with ruler and compass? The answer is yes. Draw an arbitrary line through the origin. With 1 as the center and A as the radius, Draw a circle that intersects the diagonal at point C. The distance from point C to I is A. Draw a line through point B parallel to IC, which intersects the diagonal at point D. Triangle OBD is similar to triangle OIC, so the ratio of the length of BD to OB equals the ratio of the length of IC to OI. The length of OB is B, the length of OI is 1, and the length of IC is A. Therefore, the length of BD is A multiplied by B. Use a compass to copy the length of BD onto the number line, thus finding the exact position for A multiplied by B. Therefore, A multiplied by B can be constructed with ruler and compass. Divided by B can be constructed in a similar manner. The result of A divided by B can be constructed with ruler and compass. Next, let's see how to perform square root extractions using ruler and compass. -1 is a constructible number, and A is a known number on the number line. Their midpoint can be obtained through addition, subtraction, multiplication, and division. Therefore, based on the previous conclusion, we can construct the midpoint of these 2 points with a ruler and compass. With their midpoint as the center, draw a circle passing through -1 and A. Draw a perpendicular line to the number line through the origin. This line intersects the circle at point C. Since the two triangles shown in color are similar, based on the corresponding proportionality, we can deduce that the distance from point C to the origin is the square root of A. Therefore, we can construct the square root of a known number using ruler and compass.